What I'm actually interested in, what I think a lot of people in engineering sciences are interested in, is some kind of dynamical process. This is going to be the generic way to maybe represent this. Now, many of you have taken a lot of courses in engineering or physics or ME, whatever you took. Typically what happened in those courses is you took a textbook and they told you this equation. If you took quantum mechanics, this equation is Schrodinger's equation. If you took E&M, it's Maxwell's equations. If you took fluid flows, it's Navier-Stokes. Right? So we're full of textbooks that tell us different Fs. And for each F, there's a whole bunch of stuff we can say. Right? And you can spend your whole career in just one F. Okay? You still can't spend a whole career doing one of these Fs, especially if you want to impale yourself on the sword of fluid dynamics and turbulence. You could do that. You can look at the graveyard of people with swords stuck through them, and you could be the next. Okay. I'd like to make fun of turbulence people because it just seems like the hardest problem in the world. It's really interesting, but it's like, wow, you could die. Okay. By the way, so how's the world changing? The world changes in the following way. I have measurements of this system at different points in time. Let's call y my measurement at some time, and I'm going to denote this by k. I got measurements. And by the way, notice the way I wrote it. It's not clear I can measure x directly. I have some measurement or a proxy for x. It could be g is just 1. So y of k is x of k. I can measure the state of the system. So part of the last couple lectures on compressive sensing was already getting toward the point which is I have a small number of measurements of the system. Can I reconstruct the system, right? This is actually the more realistic case. If you're, for instance, trying to understand ocean circulation and you want to do measurements on there, you're not going to get a full state estimate of the entire ocean, right? You're going to have maybe some buoys, and they're in certain places. So you're getting a small snapshot of everything that's going on. Does that make sense? Okay, that's more realistic. If you do neuroscience, you put probes in a brain. Okay, these forks, I think people do like, maybe hundreds of neurons at a time now. How many neurons do you have? I mean, mine might be a little lower than yours now because, again, I'm past a certain age. But let's still say that I'm in the billions, and I took 100 recordings, and I'm going to tell you how I work. I'm much more complicated than that. Okay, so the point is, you have a very limited set of recordings typically on a complex system. So that's kind of the situation you're faced with. You have a recording of something. More than that, just because you measured it doesn't mean it's the right variable. Okay? What is the right variable? We're going to talk about that a little bit in these lectures. Okay? But I do want to emphasize, just because you measured it, oh, I measured the temperature of this system, or in brains, I measured the voltage of what's going on with neurons. That doesn't make it the right variable to characterize your system, or the best variable. It is a variable, but there might be better ones. Okay? So how's the world change? I told you already, we have a bunch of textbooks with this. But now, we have more complex systems, we understand other kind of systems, and it's not clear I know what F is. So I'm measuring a new system. We don't have necessarily governing equations, but I got a lot of measurements. Okay? So now I have this, and I don't know F. But I'd still like to say something about the system. Is everybody good with where I'm going with this? I don't know what f is. That's where I'm actually really trying to get to, is like, I'm measuring a system and I don't know its governing equations. This tends to happen especially in multi-scale systems, where there's all kinds of physical effects, and yet there's these emergent properties out of the system, and I can't necessarily write down an equation for them. I don't have governing first principles. And so I don't know what f is, but you know what I still want to do? I want to predict the future. I want to characterize the system. Okay? Good? All right. You guys seem super excited about this. I can totally tell. Could be this Friday morning. You're looking forward to your parties tonight. That's what 20-year-olds should be doing, not getting up at 6 to work out at the gym. They should be ready for parties tonight. I'm supposed to encourage that, right? Or not? I don't know. So we're going to talk about a couple ways to head towards this. The first methods we're going to hit, and it's going to be happening here in the first set of lectures, is what's called dynamic mode decomposition, or DMD. DMD. I'm dino. Okay, not quite. You guys good? Okay. Nobody AC/DC fan? Come on, Angus died this year. You should at least give him some love. Don't know who Angus is either. So sad. Come on. You know AC/DC? Colin, come on, give it. Don't act. You're going to tell me you don't. I was born in the 90s. I'm going to go home and go to bed again. All right. They transcend the 90s. They are like, okay? I'm going to like just, can we like set it up so that my theme song for the video is like a little AC/DC? Back in Black? No response. All right. So DMD, we're going to work on that. And what it's going to do is, that's the first thing we're going to do. The second thing we're going to do, and that's going to be next week, is what's going to do, we're going to try to actually discover nonlinear dynamics. And that's going to be what's called sparse identification of nonlinear dynamics. So we'll cover that next week. But here, what DMD is going to try to do, it's going to be very much like PCA in a way, which is going to try to find low-rank structures. And we're going to basically try to say, well, I'm going to have a hard time getting a nonlinear dynamics. But my goal will be, as I take my data, maybe I can approximate this with a linear dynamical system. What I really want to do with that linear dynamical system is to say, I want to approximate it with the best possible linear dynamical system. And when I say best possible, that typically means I've done some kind of regression somewhere or an optimization, right? So when I say best, that means there was something I did best to, and that is going to be a least square fit to the data here. Okay? So let's talk about how we might be able to accomplish such a feat. And by the way, why would I want to do that? So let's talk about this system here. This is my goal, and I'm going to drop the vector sign. So I push my bold on my pen so you can all see it, right? All right. So here, what I have is a system, and typically what we think about is X is some high dimensional space. So X, exists in some big. So when you solve a partial differential equation like Navier-Stokes, or you measure brain data, right, all the points everywhere, I just put it all into a vector. So fluid simulations, this would be 1 billion degrees of freedom. Okay? That's why this kind of can be helpful for you. So oftentimes, this thing will be just huge. So let's draw this. So just imagine it's very, very big. Okay? So this is the state of the system. Okay? So we're not looking at a 2 by 2 or a 3 by 3 differential equation. We're looking at something that's massive, typically. All right. So what are we going to do with this? Well, the nice thing about a linear system like this, if you remember back to your undergraduate, differential equations, there was a very simple way to solve this, which is to say, hey, let's let x be v e to lambda t. The whole differential equations course was just say, let's just throw in an exponential solution. That's all you learned in that class. If you actually go back to it, you think, oh, I learned all these things. No, you didn't. You learned one thing. We just repackaged it to try to make you think you learned all kinds of things, but you just learned that. And you shove that in there, and what do you get? Well, that. Eigenvalue problem. That's it. And then you said, oh, great. So I can solve for eigenvalues and eigenfunctions out of this thing, right? And let's go ahead and say that I have some eigenfunctions here. So my eigenfunctions, let's call them phi of j's. And they each have an eigenvalue, lambda j. So presumably you guys know how to find eigenvalues and eigenfunctions. Okay? And that's all you do is you say, well, okay, so take this to the side. I want, in this case, the determinant to be 0. The determinant is 0. Gives me a characteristic equation to determine the lambdas. For each lambda, I get an eigenfunction. Okay? So that was actually the whole point of differential equations as an undergrad. And the only thing we could actually solve in that class, for the most part, was constant coefficient differential equations. And then once we found solutions, we could force it and maybe get a particular solution to glue onto our homogeneous solution. And that's the whole structure of the course. Okay? So I summarized in 5 minutes what you learned in whatever 10 to 15 weeks. Okay? But that's it. So the nice thing here then is once I have this, these represent a basis that I can now expand the solution in. In particular, remember that v is this here, so my solution starts to look like the following. Essentially, it is a sum b of j, phi of j, e to the lambda j t. J equals 1 to whatever, n. I have an exact solution. So that's kind of the awesome thing about linear systems. Why do we like linear systems? Why do we always work so hard to try to make things linear? Is because I can write down a solution. I have general techniques for solving linear systems, dynamical systems. The minute you make it nonlinear, there are no general techniques. Every single nonlinear system may have a different strategy. It's a little bit like, think about solving a linear system of equations. If the determinant's not 0, there's one unique solution. As soon as they give you a nonlinear system of equations, there could be no solutions, infinite solutions, 13, 5. There's no general rule. Every single one is different. Do you see this as a problem? Because you're actually trying to solve a system, say, I kind of have to have some confidence that I didn't miss 15 of the solutions that really maybe matter. Linear systems, you can say everything about them. And you have a general solution. Okay? So this is why we want to do this approximation to a linear dynamical system. Everybody good with that? All right. Make things linear. It's just like a good principle in life. Okay? You have a problem, and if you can make it linear, make it linear. It'll help you out a lot. Okay, so this is going to be our dynamic mode decomposition idea. The question is, how do I actually find such a system from data? Okay? Remember, part of the objective here is what I have is measurements of my system. I don't know what f is. So it's not like I can get a from f. I don't know what f is. All I have is data I'm collecting. Okay? Good? That's going to be our constraint. All right. So let's do it. So for the moment, what we're going to do is assume that I actually have access to full state measurements. So I can measure x directly. Okay? So here's what I'm going to do. I'm going to show you how easy this is in a way. I'm going to say I can measure x at any time point. So remember, x of j is the state of the vector at the jth time point. Okay, some high-dimensional system. Typically, it's high-dimensional. It doesn't have to be. Okay, all right. And so what I'm going to do is I'm going to make a big matrix, capital X. The columns of capital X are going to be time snapshots of this thing. Okay? So, for instance, it's going to be x1, x2, all the way to x of, let me make sure I get this right, m minus 1. So I just sit there and measure the system, and it's snapshots. Okay, got my thing measuring. Yeah? How it's evolving in time. I'm going to make another matrix. X prime. And what this matrix is, it's going to look almost identical, except all the columns are going to be shifted over. So I'm going to start the first column with x2, x3, all the way to x of m. This is a purely data-driven way to get this system. All I got to do is take measurements. I don't know what the dynamics are. I'm just going to record and build a model. How's it going to happen? Well, I have these two matrices, which just come from recordings, right? And we'll talk about how long you have to record for. There's actually a lot of different strategies around this, right? So there's a lot, just like your homework, there's a lot of like, well, how do you know how many m you should do? Or how many? It's all a little bit of massaging at the end, okay? That you have to figure out, and it's problem specific. All right? But here, two matrices. Just turn on my sensors, got them. So what's my objective? My objective is to build a linear system, a linear dynamical system, right? My goal is to build this. And the way I'm going to do that is to say, like, well, basically, if I want to build this linear dynamics, I'm looking for a matrix that takes me from where I am to the future state. So one way to think about this is I want the best matrix that when I multiply x, it takes me to x prime. We will ponder this for a moment. What this says is if I hit A with x, I get x prime. So what it's saying is I'm trying to find a matrix that if I hit this matrix, I come in here, it means x1 goes to x2. x2 goes to x3. So in other words, the only difference is x1 is advancing delta t into the future. x2 is advancing delta t into the future. That's essentially what the differential equation tells you, is how do you advance into the future. And so what this is telling you is here is the mapping from going from where I am now to delta t into the future. It is the operator that takes me to the future, delta t. Everybody good with that? All right. Stated like that, super easy solution. All you got to do is multiply, okay, on the left side, right side, by the pseudo-inverse. So the pseudo-inverse, denoted by this. So x times its pseudo-inverse is identity. And so you just get A is equal to x prime x pseudo-inverse. The pseudo-inverse is a least square regression algorithm. It's called the Moore-Penrose algorithm to compute a pseudo-inverse, just as a least squares to get that. It's fast. And what it's telling you is this matrix here is the least square fit for, notice, okay, real quick, the matrix A that best gets me from x1 to x2 is different than the matrix A that gets me from x2 to x3, generally. In fact, if I was trying to fit all these, I'd have a bunch of matrices A. I'm looking for the one matrix that kind of best does all of them. with the smallest least square error. That's the matrix. Okay? So that is what you want to compute. You take your data snapshots, you build this A. That is, in fact, going to be the basis for saying, oh, then I have my dynamical systems. Because now I take that matrix A, and what do I do with it? I do this with it. Once I have that, I can say, like, oh, just go find the eigenvalues, eigenvectors, and these are going to be called DMD eigenvalues, DMD eigenvectors. Okay? Now, here's the thing. There's a problem, so let's leave that there. That's what's called exact DMD. There are other ways to get a DMD approximation, but this is the easiest. So let me just label this exact DMD, and I'll go through the algorithm in a moment. Okay, but this is kind of the philosophy. Everybody good with that? Just a regression. Okay, yes? Okay, good question. The way I wrote it here, they are, right? All you really need, so these could have different variable step size between them, but in the exact DMD, this to this has to be all wherever I took these measurements, they have to be delta t advanced. So this could be time 1, 10, 11, 38, but then they all have to advance delta t, the same delta t. Okay? However, we have a generalization of this called optimized DMD, which allows you to take any time snapshots between things. That's, again, MATLAB code's up online. The paper is actually coming out just now on optimized DMD, which allows you to have general stepping. There's also a robust DMD, which allows you to do this and say, yeah, but what if I have this? Remember, we talked about robustifying your statistics. What if I have a bunch of outliers that are really throwing things off? So there's a way to do this so that you get rid of outliers, allow for general stepping. So there's also a robust DMD. Okay? That's up on the archive if anybody's interested. Okay, so that's the idea. So now let's talk about some problems with this idea, and then we'll talk about the algorithm, and then we'll program. What did I say about the vectors x? High dimensional. So in general, that matrix X is this. It's big, tall, skinny. And then the pseudo-inverse of this thing looks like this. So when I take the outer product of that, here's what my matrix is. Absolutely massive. So for instance, if I had 1 billion degrees of freedom, this would be a billion by billion matrix that I'd have to find eigenvalues and eigenvectors for. It's a stupid thing to do. Okay? Now, why is it stupid? There's one fundamental dogma in this class that runs throughout. It's kind of my own dogma personally. It's like all these systems we're measuring show low rank structure. That's why data science exists right now. Because almost any data set, from Amazon databases to fluid flow to neuroscience, all of them exhibit low dimensional behavior in these high dimensional systems. This says, it just completely ignores the fact that there's low rank structure. So instead, we're going to say, like, all right, this is a bad idea to just compute that pseudo-inverse and eigenvalues. So instead, we're going to define an algorithm. Here's going to be the algorithm. I want to compute this matrix, right? So first of all, let's talk about our data matrix X. We may or may not get to coding, so I don't want to rush the coding, so we might actually push that off to Monday. I know it's going to be super hard for you on the weekend to not have seen this. You'll be so disappointed. You'll feel restless the entire weekend. It's just tough. Go work out. You'll feel better. Okay? But what are we going to do with the data matrix? It's big. Thank you. Yes. Kind of like most, I don't know, SVD it. Like that should be your generic. What are you going to do with this matrix? I don't know, SVD it. Yeah, it's a good idea. It's always a good idea. It's always the right answer, usually with me. Anyway, okay. SVD it. And I know I can because I have guarantees. Now, why am I doing this? What I'm going to do is I'm going to do this decomposition. But right away, when I do the decomposition, I'm going to think about the fact that low-rank structure exists in the data I'm going to look at. And so I want to start producing a model and taking advantage of the low-rank structure. Okay? So for instance, if you are measuring fluid flow and you do have a billion degree of freedom system, you don't want to be building that billion by billion matrix. It'll crash your MATLAB. But also, a lot of times, just like when you looked at those Yale faces, high dimensional, they all collapse down to like 200, 100, right? You can get most of the information out of 200 modes. Same thing with fluids, even turbulence. 200, 300 modes, truncate, you can represent almost any fluid flow with it. Why work with a billion when you can work with 200? Okay? That's a philosophical viewpoint I think you need to make sure to take in a lot of the data you work with. Go low rank when possible. Okay? So that's the first step. We're going to go low rank. I've already set it up to do that. Okay? So one way to think about this is I'm going to make this explicit to put R, R, R. So we are looking at a rank R truncation. Now, where you truncate is kind of an interesting question. Let's ignore the truncation issue for a moment, where I would want to truncate. But if I had fluid flow, there would be some point at which I'd look at what I'd do first. Remember, we always do it. You go plot that thing. You plot the singular values and say, where should I truncate? Oh, you make a decision based upon what this looks like. Okay? And then you say, okay, I'm going to keep R modes. That is going to be the subspace I'm going to work in and build a model in. Those are directions that are optimal because it's an SVD. Optimal in all 2 sense. Okay? Everybody go with that? So that's step one. Not a terrible surprise, given the nature of the course so far. There's always an SVD involved somewhere so far, right? Pretty much. There's been an SVD lurking around, and so we take advantage of it. And again, there's a reason for that. The SVD gives you the optimal low-rank embeddings, so it always shows up to play a role. All right, step 2 of the algorithm. Let's go back and look at this thing here. A is equal to x pseudo inverse. That's what I was trying to work with. So what I'm going to show you is that you say, well, okay, I could, if I was working with this directly, I'd have to compute the pseudo inverse of this. And the pseudo inverse of this, right, is if you take the inverse of this, switches the orders, and then you have to take inverses of u, but the inverse of u is easy because it's unitary, right? This becomes u star. The inverse of v star becomes v. This just becomes sigma to the -1. So it's very easy to compute that inverse. And so this thing here becomes okay? So this is one way to view what we're going to do. So this, remember, so I said we're going to work with this, but for right now, if we didn't, this is what we'd have to compute, and we could do it through here. But really, again, part of the objective here is not to work directly with A, because A would be massive, but to work with a similarity transform of A. So I want to pop all of A down to the low rank subspace. How do you do that? I'm going to work with a matrix A tilde. And the A tilde matrix looks like this. This is a similarity transform into a new set of variables. And these new variables are the U variables, the low rank embedding space. Okay? This matrix A is n by n. This one here would be r by r. So this is a billion by a billion. This might be 200 by 200 if I truncate it 200 modes. You can decide which you prefer, but I prefer this. Okay? And in general, for large-scale problems, so a lot of things, too, to think about. In general, what's some of the problems we have with data science? So let me tell you some of them. Let's talk about neural recordings. You know, they can put the stuff in the brain, and they can record, in some of these sensors, at many kilohertz. So every single second, and they record for minutes or hours. So just think about it. I'm recording at 20 kilohertz. I have 20,000 time points per second, and now you give me an hour of data. That's our big data problem, right? All right. Or you have a billion variables, and you record this in time. So you can get very quickly out of hand with data. The whole reason we do stuff like this is because if you're having really big data, there's low rank structure, most of your data, you got to collapse it, or else you're just not going to have a big enough computer. It does not take much for you to basically run out of the memory on your laptop, or even on a machine cluster in your lab, or even on the Amazon cloud. Have you done computing in the cloud, Amazon cloud? It's kind of expensive. You know, say, oh, just do everything on the cloud. Yeah, and then you get your bill. We did this. We were like training a deep neural net. It's like, yeah, let's just do this. It shouldn't be so bad. $10,000. Are you serious? I should have bought a machine for the office. It would have been cheaper. So we stopped. We said, okay, let's think very carefully about what we want to do. Why? Because it's this big computation. And this is the problem you have with data. Okay? In general, if you notice, most of the problems that we're going to be doing are sort of moderate scale. They all can fit on your laptop. I gave you 1.5 gigs of video, but broken up into a bunch of parts, so each one you can like pull stuff out, then it becomes pretty small, and then the SVD is super simple on those, okay? So this is this whole idea. Get yourself into a better space, okay? Now, notice what I have here then is U star, AU, so A times U. So if I have the AU, well, here's what A looks like. U star U is identity. It's out because it's unitary transform. Then I get X prime V sigma minus 1. This is the matrix A tilde, my reduced rank matrix A that matters for my dynamics. So I've taken my space, I've done the SVD, found the low dimensional space, built the model there. Okay? Step 3. Exercise and eat well. Okay, just see if you're paying attention. All right. No. Do an eigenvalue decomposition. That's going to be our next step. Remember I said, hey, we have a matrix A, you just do an eigendecomposition. Now we're back in familiar territory for you, right? Presumably you've done eigenvectors and eigenvalues of different things before. It's now on your home turf. Outside of everything we've done, all you're going to do is remember that we're going to say, well, how you'd solve this, you wrote down eigenvalues and eigenvectors, and so you say like, okay, same thing here. That's the generic form of the eigenvalue problem. So, you know, you get R eigenvalues, R eigenvectors. The R eigenvectors are sitting in W. So the W, the columns of W are the eigenvectors. And this matrix big lambda are the eigenvalues. Eigs command in MATLAB. Okay? Final step. I'll have to erase some board, huh? All right. All right, I'll come back over to here. So, by the way, notice what I'm doing. In some sense, I'm defining the DMD as an algorithm. And this is exactly how it was originally defined. People were looking at fluid flow. They were trying to do prediction, and and it was a very complicated fluid problem. And so they're saying, but I have recordings of the data. Can I build a model that will allow me to predict the future state in some kind of efficient way? And in fact, they said, well, just start taking snapshots of the systems, build a linear model that gives you a future time prediction pretty nicely, and we'll talk about that in a minute. And as the dynamics changes, you can just keep changing the matrix A, right? You can just update the model as you go along. The nice thing about this, it's kind of like a low commitment thing. The model changes, and you're like, no big deal, I'll just build a new one. I can just keep updating A as I go along. Because a lot of systems change on you. So if you commit to a model and it goes bad, you got to like, oh, I got to build a new model. This says, I'll build one for you as we go. In fact, I could do it on the fly as it goes along. Okay? So that's something pretty nice, especially for parameterized systems where parameters are wandering on you. You need something that can handle that. Finally, step 4, get yourself back into your high dimensional space. So essentially, the route back, remember we're in an R-dimensional space, the route back up to the high dimensional space. Remember, you want eigenfunctions, DMD modes and DMD eigenvalues back in the original coordinate system. I've compacted everything down to you, but then when I want to plot for you, let's say the fluids flow, I have to give you back a plot in n-dimensional space. Okay? The last step of that is to go back through this process. It's this. Here. Okay? So that's it. These are now the DMD modes. The eigenvalues don't change. That's just in the that's just part of what you have there. So at the end of the day then, you calculate some eigenvalues, you calculate some eigenvectors, the DMD modes. And by the way, here's what's kind of interesting. I'll just point this out to you. This is very important actually, some important facts. 1, when you come down to this low rank subspace and you build these vectors, notice, even if they were orthogonal here, when you go and project them back up here, DMD modes are not orthogonal. There's good and bad in that. When you do an SVD, the requirement is that all the columns of U are orthogonal, which is fine, except for there's some problems where there's actually some advantage to not having orthogonal modes. Okay? You may want to say like, hey, what if I had a problem? Again, we already talked about this from independent component of analysis, right? If you had something going on over here and something going on over here, right? SVD would say like, oh, I need orthogonal modes, so I'll build 2 modes like that. Those are the 2 best modes. When in fact, you should probably like build one there and there. ICA lets you do that. So does DMD. It's not restricted to orthogonal modes. And there's some great advantage to that at times. Okay? Just want to throw that out there. All right? And now you actually have a solution. And the solution is the following. X is equal to, this is your model, DMD modes. This is a matrix times B vector. Okay? So this is equivalent to k equals 1 to r, the different eigenvalues e to omega kt b of k. So this is in matrix form. So this is all the eigenmodes together. And this is a diagonal matrix exponentiated there with the eigenvalues that you had. And B is essentially the loading of, how do I get B? I don't know what B is. I have this, I have this. These are DMD eigenvalues, DMD modes. You say, well, okay, what about at time 0? At time 0, I have this. E to the 0 is 1, B. Oh, X equal to B. because I presumably know the state here. So this is AX equal to B. So I can say, oh, B is easy to compute. I could compute it. There are other ways to do this, by the way. This is actually, let's say, a fancy step that we can improve on. But for right now, let's just say, if I have that, I can backslash. Right? So it's going to be A backslash B. I got B. I can put it in there. And now, I have X of T. Now, what's the big deal about this? The big deal about this is because I have a linear model, here's the solution to that linear model. I say to you, I take snapshots. Tell me where the solution's going. Tell me where the solution is going to be in 3 delta t's from now. Just put in the time. You wanted it. What's the prediction of the solution at time 10? Put in t equals 10. There's the solution at time. There's my prediction of the solution at time 10. Does that make sense? I have a way to predict the future without actually running a differential equations model. I just plug in. Okay? That's very powerful. This will only give you, usually, some kind of short time window into the future of a good prediction. Why? Let's talk about eigenvalues. What if there is an eigenvalue? Here's the real part of these things. I'm going to call these omega. Imaginary part of omega. What if there's an eigenvalue right like there? Slightly positive. What's it going to do as you go forward into the future? It's going to exponentially blow up. In fact, if any of those eigenvalues just have a slightly tiny bit of real part, it's going to blow up. The system doesn't do that. It's just that when you did the regression, remember, this is just a regression. Okay? It's a least square fit. And that least square fit says, here's the best model currently, and yes, you have eigenvalues that are slightly over there, and you're going to blow up. That's okay. Maybe I don't need to know what the solution is going to look like in infinity. I just need to know 5 units into the future. Now, why is this important? It's important for one really important reason, in addition to some others. But remember, what I just built for you from data, without knowing anything about the physics, I built for you a model that currently, this data seems to be obeying that. And it allows me to do a future state prediction. And in a lot of systems, especially if you're an ME, AA, everybody has control courses, right? I can do the same thing with actuation. So the biggest deal about control is you have to say, my system's going over here, I have to actuate it to make it go where I want. So you can set this thing up. Control theory works in linear systems. That's where we have all the guarantees. As soon as it's nonlinears, all bets are off. But it's linear, it works, and what I've just built for you is the best linear model right now, which means I could potentially control it.